I'm Dr. Colin Campbell, and this is a Meter Chalk Talk. Today, we're starting on part 3 of view factors, trying to understand the implications of direct beam radiation. We're going to look at a couple examples generally, and then we're going to get down into the details. Here's our equation we've been using all along, but today we're only going to study one small part of it, the FP, or the view factor for perpendicular radiation. I've drawn a little diagram here to show what that looks like. The radiation source that we're going to be typically using is the sun, so my diagram includes the sun and maybe a leaf of interest. Today, we're back talking about the absorbed radiation equation, but now we're only going to focus on one particular part of that equation, this variable FP. This is the view factor for perpendicular radiation. Now, if we measure the radiation coming into the system right here, that radiation we'd actually call SP. That's the radiation that's actually hitting a perpendicular surface. But most of our objects we're interested in aren't going to be perpendicular to the beam of radiation. So if we were considering this leaf here, this radiation as it comes in is actually going to spread itself out over that leaf, and so there'd be far less radiation per unit area on that leaf than there would be on a perpendicular surface. And so we're interested in that direct beam radiation, and that's described as the average radiation flux density over the entire surface of an object of interest divided by the flux density on a perpendicular flat absorbing surface facing the radiation source. So how do we actually go about calculating it? That's what we're going to talk about now. There are two relatively simple examples that we can work on. The first example is the easiest. It's just a canopy. To calculate FP, we simply look at the cosine of the zenith angle of the radiation. The second case we're interested in is that of a leaf. Now, a leaf is a little more complicated than a canopy. This may be a little bit confusing, but to us, in the radiation world, a canopy only has one side. It's facing the sky. We already talked about that in one of the other discussions we had. For a leaf, there are actually two sides. When you think about it, you can look at the bottom side of a leaf and the top side of a leaf. When we have radiation coming into the system, it's only going to hit one of the sides of that leaf. So if we want to calculate our view factor for perpendicular radiation, because there are two sides, let's say 30 centimeters squared, only 15 centimeters squared is going to be impinged by the radiation. So we have to multiply that cosine psi by 0.5. So that would be how we calculate the view factor of a leaf for perpendicular radiation. The third case is a bit more complicated. Here we're going to talk about animals. So for an animal, to calculate the view factor, we have to take the ratio of the projected area divided by the actual area. So I've tried to draw a diagram here to show you what that looks like. So let's say we had this object of interest. Now that's just a cylinder here. That's fine. When we talk about our actual animals, they're not exactly cylinders, but that's actually how we're going to approximate them. So wait for that in a minute. Here's our radiation coming into our object. This is the area of the object here, and there's the projected area here on maybe the ground surface on which that object is sitting. Now, the radiation is going to impinge on this area right here. Again, with our projected area, if we put that here, and the area that actually is covered by that radiation right there, we get a value of AP over A. AP over A now is equal to our FP. The range of AP over A goes from about 0.1 to 0.3, depending on the angle with which the radiation is impinging on the object and the size and shape of the object. We're going to consider 3 of them. Now we're going to talk specifically about some shapes of animals and how to find their view factors. Be a little patient here. This may seem a bit complex, but at the same time, we are going to do some simplifications which should help. So the first thing we need to do if we're finding an object, specifically an animal's view factor, is decide what that animal looks like. And every time I teach this in class, people think it's pretty funny because we're going to break up our animals into prolate spheroids. Imagine I had a sphere and I just squished it. That's what a prolate spheroid would look like. The other two are a little easier to imagine. Just a cylinder with flat ends or a cylinder with hemispherical ends. Now, it turns into a pretty big joke with the students when they're talking about, well, is a pig a cylinder with a flat end or a round end? And you can decide that for yourself. When we do that, we need to know a couple of different things. So let's start talking about it. For a prolate spheroid, we simply need to know a couple of things. First of all, the diameter of the sphere, that's here A, and the height of the sphere, that's B right here. When we know A and B, and we also know the angle with which the radiation impinges on that object to the longitudinal axis, so that would be this angle right here, then we're able to go to this graph and actually figure out what AP over A is. So let me just show you that. Say we had an example down here of a sparrow. This sparrow was about 4 centimeters in diameter, and it's about 2.5 centimeters tall. We divide one by the other and get about 0.625 for this ratio of B over A. That B over A ratio just goes into this table. That's between 0.75 and 0.5. And then we just follow it through here. And we look for the angle down here that matched up with our solar elevation angle. Okay, and because this is actually, here's the horizontal axis. Of course, we have the sun. Typically, this is our zenith angle. We're actually looking for this angle right here, what we sometimes call theta. So I just noted that here, if our zenith angle was 30, our elevation angle would be 90 minus 30 or 60. We go up to the table here, or the graph here. We go up, find that approximate spot, go over here, and as I've shown you here, the FP would be around 0.26. So not all that hard if we can make a good estimate of the height and the diameter of our prolate spheroid. The two other examples are actually pretty similar. One has 2 hemispherical ends on it and the other just has flat ends. So I'll take you through one example. You probably should be able to kind of walk your way through the other example. Again, the critical piece is this longitudinal axis that we're showing right here. Now, a human being may look a lot like a cylinder to this analysis, but that human being would of course be a cylinder that is standing up. So you'd have to change the angle with which the light approached, or the radiation approached, that longitudinal axis. So please make a note of that. Now, if we go to the diagram here of this cylinder, we have H, which is the height along the longitudinal axis, and then we have this value D, or again the diameter, across the diameter of that cylinder. Let's take a case like the dog. Now, I don't know exact measurements of a dog, so I'm just going to throw some guesses out there. Let's say this dog was 60 centimeters long in the longitudinal axis and about 20 centimeters high. Okay? Now, if we took our 60 and put it right here in the height, we took 20 and we put it right there in the diameter, we'd simply divide those two things and we get a value of 3 out of that H over D calculation. Again, like the prolate spheroid, we'd simply go back into the equation and plug it in for one of these lines. Again, these are just models of those lines, and it ends up that we're between the 2 and the 4 here, and we can just guess at where we might end up. Now again, if we had the same solar elevation angle and zenith angle as we did in the last problem, life gets still pretty easy because it comes out to be 60 degrees elevation angle, and all these lines come together there. So again, we go back here, the value of AP over A is 0.25, and that's our view factor for the cylinder with flat ends. I do note over here the same exact process by which we get the analysis of the FP for a cylinder with hemispherical ends. It's just a little bit different. We maybe get a value out of this table. Well, we've got the pig here. We got a 120 centimeter long pig, and it's 30 centimeters in diameter. Now we've got an H over D ratio of around 4. Again, we come back to that line and we get a value here of about 0.27. I did it 0.26 in the example. I'm going to do a quick summary of what we've learned in this chalk talk. We need to calculate the view factor for perpendicular radiation, and there are 3 cases we've considered to do that. First of all, the canopy case, where FP is a very simple calculation of the cosine of the zenith angle. Pretty straightforward. Then there's the case of the leaf. We learned that the leaf has 2 sides. Now we're multiplying the cosine of psi by 0.5 because there's 2 sides of the leaf, so you're hitting only half the surface. The third case was the more complicated case. This is the case of an object, particularly an animal that's on the surface, where we're trying to calculate its FP. That, we learned, is the projected area divided by the area. To calculate AP over A, we learned that we need to find the height and the diameter of our object if it's a cylinder or cylinder-like, or if it's a prolate spheroid, we need to collect the values A and B. We can put them into these graphs that I showed you and get out a value of FP. A little more complicated, but we can still do it. After all that discussion, we're back to the absorbed radiation equation. And for better or for worse, we only calculated one parameter in this equation right here, the FP. Now we're going to get the SP, just like I showed you in another chalk talk, and we're going to be able to calculate the overall absorbed radiation of our object, our canopy, our leaf, or whatever we're interested in. Thanks for watching this Meter Chalk Talk. For other videos like this, check out our YouTube channel or go over to metergroup.com where you can find a lot more great content. See you next time on our Meter Chalk Talk.